Okay, so that's proof that the dual program is a convex program. So obviously, the only thing that we need to worry about is the objective function. So that f be the negation of the objective function. Because previously we want to maximize negative 1/2 of blah 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 plus the sum of lambda I. If we want to maximize the concave function, we need to minimize that some kind of convex function. Okay, we want to show that this is concave, so let's show f is convex. Okay, so given the function f, now if we want to show that this is convex, we want to find its Hessian matrix. Okay, and for Hessian matrix, we are doing second order derivatives, so obviously the last term would disappear. Now for this term, whenever we differentiate it with respect to lambda I and then lambda j, we're going to take away this and that, of course. And also, you may see that this is pretty much the sum over I and j, okay? So for any I and any j, you only have this particular term remains if your lambda I and lambda j satisfying I and j. Okay, so whenever you have, for example, you differentiate this whole thing with respect to lambda 1 and lambda 2, then what you're going to obtain is that you only have the last term remains. Okay, that's how you get your Hessian. So all we need to do is to try to show that this particular big matrix is positive semi-definite. Oh well, there are a lot of things, and doing that principal, leading principal minors, whatever, seems to be very difficult. So let's use a slightly different technique. So the thing is that you may observe that this is really a very some kind of regular matrix. Okay, and after some careful observation, you may see that whenever you are looking at a term, for example, this guy, you may always split it into y1 x1 transpose as one thing, multiplied by y2 x2. Okay, so eventually that allows us to split the big matrix or to factorize this big matrix into two matrices. Okay, this one and that one. So the first term here, for example, is y1 x1 transpose times y1 x1, and so on and so on and so on. So here, each value here is actually a vector. Okay, each value here is actually a vector. For here, a column vector. Okay, and that's why this is a column, this is a column, this is a column. Your z, which is defined in this way, your z is actually an n by m matrix. Okay, so you may factorize this Hessian matrix into into a product of z transpose times z. Okay, and once you do that, now if we want to show that the Hessian is positive semi-definite, we use the definition. Okay, so it's interesting. Here we don't use those properties like principal leading, leading principal minors or eigenvalues. We use the definition. The definition is that if you have a matrix A which is positive semi-definite, this is defined in a way that X transpose AX should be non-negative for all possible X that is of appropriate dimensions. Okay, if this is the case, A is defined as positive semi-definite. So now that we see whether we have this X transpose AX, this Hessian can be decomposed into Z transpose Z, and then you see that X transpose Z transpose is indeed ZX transpose. All right, and that means we are actually doing the vector ZX. We get the vector ZX take the norm and then square it. And obviously, this means we have a non-negative term here. Okay? And this is true, whatever z you have, whatever x you have. That's how we prove the fact that our dual program is indeed convex.